If there's one material that defines modern engineering, it's steel. Accounting for over 90% of global metal production, the overwhelming dominance of steel comes not just from its strength and affordability, but from something unique: its ability to be transformed through heat treatment. Take these three steel parts. The first is soft and ductile, the second is very hard and brittle, and the third is strong and tough. But they all have the exact same chemical composition. The only difference is they've been heat treated in different ways. This ability to control and fine-tune the properties of the material through precise heating and cooling really is the superpower of steel. So let's see how it works. First, the ingredients. Steel is an alloy of iron and carbon, and usually a few other elements in small proportions. Steels are classified based on carbon content, as low carbon, medium carbon, and high carbon steels. Anything beyond that, above 2.1% carbon, is called cast iron. If a steel contains a significant amount of alloying elements, above around 1%, it's called an alloy steel. Otherwise, it's a plain carbon steel. To understand how heat treatment can transform the properties of these materials, and the effect different carbon concentrations can have, we first need to look at the main ingredient, iron, to see how it behaves at different temperatures. Pure iron goes through several changes as it's heated. At room temperature, the iron atoms are arranged in a body-centered cubic form, BCC, with one atom at each corner of the unit cell and one in the center. This is called ferrite. Above 912 degrees Celsius, iron becomes more stable in a different atomic arrangement and undergoes a phase transformation. The atoms shift from a body-centered cubic structure to a face-centered structure, where atoms are packed more closely and efficiently. This FCC form of iron is called austenite. Let's visualize the phase transformations of iron on a graph. The ferrite to austenite transformation happens at 912 degrees. As temperature keeps increasing, iron changes back to ferrite at 1394 degrees, before melting to a liquid at 1538 degrees. These different solid phases are called allotropes of iron, and for convenience, a Greek letter is assigned to each one. Now let's see what happens when we add carbon. We can extend the diagram to show how the phases within the material change with different amounts of carbon. This is the phase diagram for iron-carbon alloys. The amount of carbon in the alloy affects the transformation temperatures, but it also introduces new phases. Because carbon atoms are small, they fit into the interstitial spaces between the iron atoms. But the BCC structure of ferrite can only accommodate a tiny amount of carbon. It has a maximum solubility of 0.02% carbon by weight at 723 degrees, which is around 1 carbon atom for every 1,000 iron atoms, and it's even less than that at lower temperatures. If the alloy composition contains more carbon than the ferrite can handle, the excess carbon atoms have to go somewhere. So a new phase called cementite forms alongside the ferrite. Cementite is a hard, brittle compound made up of 1 carbon atom for every 3 iron atoms. Austenite can hold a much larger amount of carbon than ferrite, from 0.8% at 723 degrees to 2.1% at 1147 degrees, which is roughly 1 carbon atom for every 10 iron atoms. If more carbon is added, we obtain a 2-phase material with austenite and cementite phases. There are several other possible phase combinations depending on the temperature and the amount of carbon. The phase diagram tells you which microstructures form at different temperatures and for different carbon concentrations. And as we'll see later on, this is the key to understanding how heat treatment works. For an alloy containing 0.8% carbon, the structure remains austenite while cooling until it reaches 723 degrees. At this temperature, the austenite undergoes a transformation from an FCC to a BCC structure, and the excess carbon the new BCC structure can't contain combines with iron atoms to form cementite. These two phases form a distinctive microstructure, consisting of alternating layers of ferrite and cementite, which is called pearlite. This composition is a special case, because the austenite transforms entirely and simultaneously into ferrite and cementite, producing only pearlite. The point on the graph at which this happens is called the eutectoid point, and steel with the corresponding 0.8% carbon composition is called eutectoid steel. In hypoeutectoid steels, those containing less carbon than the eutectoid composition, some ferrite forms before the eutectoid temperature is reached. On further cooling, the remaining austenite transforms into pearlite. The final microstructure ends up being a mix of pro-eutectoid ferrite and pearlite. In hyper-eutectoid steels, cementite forms first, as the austenite cools. At the eutectoid temperature, the remaining austenite transforms into pearlite, so the final microstructure is a mix of pro-eutectoid cementite and pearlite. All of these transformations rely on diffusion, the movement of carbon and iron atoms through the lattice to form new phases. Because diffusion takes time, the iron-carbon phase diagram only represents equilibrium conditions. It assumes cooling and heating occur slowly enough for the atoms to fully rearrange into the most stable phases. But it can take minutes, hours, or even days for austenite to fully transform into ferrite, depending on composition and temperature. The time it takes for a phase transformation to occur can be determined through testing. A small sample is heated until it's fully austenite, then rapidly cooled to a target temperature and held there for a set amount of time. After this hold, the sample is rapidly cooled to room temperature to interrupt the transformation, and the microstructure can be examined to get an idea of how much of the austenite has turned into ferrite and cementite. By repeating this test for different temperatures and holding times, you can start to map out the relationship between time, temperature, and the phases that form in a given steel. This is called a time-temperature transformation, or TTT diagram. The dashed line at the top of the diagram marks the equilibrium transformation temperature. At temperatures below this line, austenite is unstable. Given enough time, it will eventually transform into ferrite and cementite. The diagram shows us how long this transformation will take if the steel is cooled to and held at a constant temperature. If this eutectoid steel is cooled to and held at 500 degrees, for example, the diagram tells us the austenite will start transforming into ferrite and cementite in less than a second, and the transformation will complete after about 9 seconds, leaving no remaining austenite. The TTT diagram is where things get really interesting, because it's where we start to see non-equilibrium phases emerging, phases that play a central role in heat treatment. The most important of these is the martensite phase. It forms when austenites cooled so rapidly the carbon atoms don't have time to diffuse out of the FCC structure to form cementite. The FCC lattice wants to transform to BCC, but can't because of the trapped carbon atoms, so it ends up distorting into a new, body-centered tetragonal structure instead, which is called martensite. The BCT lattice forms almost instantly, growing out from austenite grain boundaries, and propagating at close to the speed of sound. This happens so fast because the transformation from FCC to BCT is diffusionless. Unlike the other phase transformations we've seen, it happens without any long-range motion of the atoms. The result is a microstructure of long, thin plates of martensite slicing through the prior austenite grains, each plate being a region where the atoms have all displaced in the same direction to form the BCT lattice. The distorted lattice of martensite makes it an extremely hard and strong, but also very brittle material. This is due to the trapped carbon atoms, which strain the lattice, locking the structure in place and impeding the motion of dislocations. The steel's carbon content has a big impact here. More carbon means greater distortion of the lattice, which increases hardness and strength at the cost of increased brittleness. On the TTT diagram, martensite appears as a region stretching along the bottom of the graph. 3 horizontal lines mark the temperatures at which martensite formation starts, reaches 50% completion, and finishes. Because it's diffusionless, no time elapses before starting or completing the transformation. It happens immediately once the temperature drops below the martensite start line. If the steel is cooled to a temperature between the martensite start and finish lines, only part of the austenite transforms, leaving a mix of martensite and retained austenite. A whole range of other microstructures can be achieved by manipulating time and temperature. A key feature here is the inflection point of the TTT diagram, often called the nose of the diagram. It marks the shortest transformation time, the temperature at which austenite is least stable and begins to transform most rapidly. Above the nose, we get pearlite, the alternating layers of ferrite and cementite we saw on the iron-carbon phase diagram. At higher temperatures, the transformation proceeds more slowly, giving carbon atoms time to move over longer distances, resulting in a coarse pearlite microstructure, with wider spacing between ferrite and cementite layers. At lower temperatures, carbon atoms have less time to diffuse, so the structure forms quickly as fine pearlite, with closely spaced layers. Fine pearlite is stronger than coarse pearlite, because the hard, brittle cementite layers are more closely spaced, creating effective barriers to the motion of dislocations. Below the nose, diffusion distances are even more restricted, which allows a different microstructure, bainite, to form. This is still a combination of ferrite and cementite, but with a much finer, more irregular mixture of the two phases. This gives bainite an excellent balance of strength and toughness, making it a target in some heat treatments. Upper bainite and lower bainite form at higher and lower temperatures within the bainite range, and have distinct microstructures. In practice, steels aren't usually cooled to a fixed temperature and held there. More often, they're cooled continuously down to room temperature. The phase transformations that occur with these more realistic cooling conditions are shown on a continuous cooling transformation, or CCT diagram. This is similar to the TTT diagram, except instead of holding the steel at a fixed temperature, the diagram is based on continuous cooling paths. Each of these curves represents a different linear cooling rate. Cool this 1080 steel from 800 degrees Celsius at a rate of 200 degrees per second, and you'll obtain martensite. At 50 degrees per second, you'll obtain a mixture of pearlite and martensite, and at 10 degrees per second, you'll get 100% pearlite. The CCT diagram shows how difficult it can be to obtain martensite. Plain carbon steels often require very high cooling rates to miss the nose of the curve and end up in the martensite region, rates that aren't achievable in practice. This is one of the main reasons alloying elements like nickel and manganese are added to steel. They shift the CCT curves to the right, so that martensite can be obtained at slower cooling rates. Unlike the TTT diagram, the CCT diagram doesn't show bainite in the area below the nose, because any cooling path that hits the nose will transform into pearlite, and pearlite can't transform into bainite without being reheated to austenite. This is another use of alloying elements. They can be added to delay pearlite transformation, which uncovers a bainite nose and allows bainitic steels to be obtained at certain cooling rates. It's this complex choreography between chemical composition, transformation kinetics, and the resulting microstructure that makes steels such complex and fascinating materials. Now we can finally get to heat treatment, which is all about using careful heating and cooling to manipulate the microstructure of steel parts to obtain useful or improved material properties. 4 key heat treatment processes are annealing, normalizing, quenching, and tempering. Let's see how they work. Annealing is used to make steel soft, ductile, and easy to work with. It's often applied to steel parts after forging or casting to relieve stresses and make the part easy to machine. The process involves heating the steel into the austenite region, then cooling it very slowly inside the furnace. Because the cooling is so gradual, the carbon atoms have plenty of time to rearrange into the wide ferrite and cementite layers of coarse pearlite, which has low strength, but is very soft and ductile. Annealing is usually a preparation step before machining or other processing. Normalizing is similar to annealing. Both heat the steel into the austenite region, with normalizing using a slightly higher temperature. The main difference is the steel is cooled in air instead of slowly in the furnace. The higher temperature helps better eliminate irregular or patchy microstructure left over from previous processing steps like casting or rolling, and the faster cooling rate produces a fine pearlite structure that's stronger and harder than annealed steel, while still retaining useful ductility. The process normalizes the steel, resetting it to a uniform, fine microstructure with good strength and hardness. Quenching is a heat treatment process that involves very rapid cooling, usually by plunging the steel part into a bath of water, oil, or other medium, depending on the cooling rate required. The objective of this rapid cooling is to produce martensite. The quenched steel has high hardness and strength, but is far too brittle to be of use in most applications. Tempering is a follow-up process to quenching. The quenched martensite steel is reheated to temperatures between 200 and 600 degrees Celsius, below the levels needed to transform the steel into austenite. It's held at this constant temperature for a defined time period, anywhere from a few minutes to several hours before cooling, usually in air. During this tempering process, excess carbon atoms trapped in the distorted, supersaturated martensite lattice diffuse out and combine to form extremely fine particles of cementite, allowing the BCT martensite lattice to relax back towards a BCC ferrite structure. The resulting microstructure is called tempered martensite. This transformation greatly improves the ductility and toughness of the quenched steel, while still retaining much of its strength and hardness, thanks to the finely dispersed cementite particles. Steel in this quenched and tempered condition is usually referred to as hardened steel. Quenching and tempering is used for critical parts that need high strength combined with toughness, like crankshafts, high-strength bolts, tools, or heavy-duty structural components. It needs sufficient carbon to be effective, though. In low-carbon steels, even if martensite forms during quenching, there's too little carbon to significantly distort the lattice, so these heat treatments produce little to no increase in strength and hardness. The objective of quenching is to cool the material fast enough that austenite turns into martensite through the entire cross-section of the material. This can be challenging with thick components, where the core of the material will take longer to cool than the surface, resulting in pearlite or bainite forming within the part instead of martensite. Hardenability is a parameter used to quantify a steel's ability to form martensite to a given depth during quenching. A steel with good hardenability will be able to form martensite more easily at slower cooling rates, and produce martensite all the way through thick sections. The Jominy N-quench test is the standard method for measuring the hardenability of steels. It involves heating a cylindrical steel sample that's 1 inch in diameter and 4 inches long until it's fully austenitic. One end of the sample is then quenched with a standardized water spray setup, creating a controlled cooling rate that decreases as you move up the sample. A flat is then ground along the length of the sample, and Rockwell hardness measurements are taken at regular intervals from the quenched end. The results are plotted as a Jominy hardness curve. Hardenability is mainly determined by composition. These different steel grades have very different curves. The maximum hardness at the quenched end on the left of the graph is governed by carbon content. The 1080 steel reaches a higher hardness at the quenched end than the 1040 steel because it contains more carbon. but the rate at which hardness decreases with distance from the quenched end is mainly influenced by alloying elements. These elements shift the TTT and CCT curves to the right, allowing martensite to form at slower cooling rates, resulting in high hardness even deep into the part. A steel like 4340, which contains nickel, chromium, and molybdenum, is a classic example of an alloy with excellent hardenability, and is a good choice for thick parts that need to be quenched and tempered. In some applications, we don't actually want the entire component to be hardened. Instead, we might only need a hard, wear-resistant surface, while keeping the interior tough and ductile. This is often the case for components like gears and shafts that experience high contact stresses, but also need to resist impact loading. Surface hardening techniques can be used on these components to intentionally create a hard outer layer, while preserving the softer, more ductile core. Induction hardening and flame hardening involve directly heating the surface of the component, followed by quenching, to create a hard martensitic layer. But these hardening methods are only effective in medium or high carbon steels, because low carbon steels don't contain enough carbon to develop sufficient hardness. For low carbon steels, case hardening techniques that actually alter the surface composition can be used instead. Carburizing involves heating the part in a carbon-rich environment to increase surface carbon content, followed by quenching. Nitriding introduces nitrogen into the surface to form hard nitride compounds, without the need for quenching. A big advantage for precision parts, since it avoids any warping that can occur with quenching. In practice, heat treatments like annealing, normalizing, quenching, and tempering are combined into sequences along with forming and machining steps. Each stage of the manufacturing process prepares the steel for the next, until the final form is obtained with a microstructure that provides the desired balance of strength, hardness, and toughness. Taking any part from concept to a fully defined manufacturing process can be a lot of work, with no shortage of engineering decisions to be made along the way, from the definition of tolerances and surface finish to the selection of manufacturing methods. Having a manufacturing partner you can trust to guide you through these decisions makes all the difference. And that's where this video's sponsor, Protolabs, comes in. Protolabs is an innovative digital manufacturing company that provides manufacturing services for every phase of the product lifecycle, from custom prototyping to full-scale production. They offer CNC machining, 3D printing, injection molding, and sheet metal fabrication, all available through a really well-designed online platform. It's easy to get started. Just upload your CAD file and select the material you want. There are hundreds to choose from. The instant quoting system gives you a price immediately, no delay or emails back and forth. You can even use the platform's real-time design for manufacturability tool to help you catch potential production issues before they become a problem. Their whole operation is optimized for speed. Protolabs can manufacture high-quality parts in as little as 1 day, which is great for quickly iterating on designs or getting your hands on that jig you needed yesterday. And if you need something a bit more specialized, like a quenched and tempered tool steel part, the Protolabs Network, a group of vetted high-quality manufacturers, will be able to get the job done, meaning Protolabs really can be a one-stop supplier for all your manufacturing needs. With the Protolabs team of expert engineers ready to provide support at every stage of the process, transforming engineering ideas into high-quality products has never been easier. So click the link in the description to visit Protolabs and make a start on your next project. And that's it for this look at the heat treatment of steels. Thanks for watching.